Hi class, so we're continuing our learning on the dot product by now doing it with algebraic vectors. So yesterday was just geometric vectors, so those are vectors that are not considered on the coordinate plane, but today we are doing algebraic vectors. So those are those which do have coordinates represented either in R2 or R3. So most of my analysis here will focus on R3. Okay, so if A is just equal to A11. So we're A1, A2, A3, sorry. So we're going to call this green vector, vector little a, and it goes from the origin to point A, which is going to be A1, A2, A3. So that's the X, Y, and Z values. And then this vector here is B. Okay, and it goes to point B, which we are going to denote as B1, B2, B3. Then just note that the red vector is vector AB. Okay, we want to find how we can represent the dot product of A dot B without using our geometric understanding. So I am going to do a little proof of this. So bear with me here. So we're going to use the cosine law to actually prove the dot product here. So we're going to represent it in a few different ways. So imagine origin AB, OAB being a triangle. Okay, then the cosine law would be the magnitude of AB squared equals the magnitude of OA squared plus the magnitude of OB squared minus 2 OA OB cos theta, okay? So what we're going to do is rewrite each of these terms in a different way and then set this equality back up with the new representations. Okay, so I'm going to use some color to kind of separate the ideas for you. Hopefully that helps. So AB, the vector AB can be represented as B1 minus A1, B2 minus A2, and B3 minus A3, okay, based on what we learned last chapter. Okay, and the magnitude, therefore, of AB can be rewritten as, magnitude of AB squared. So normally for the magnitude, we would have a huge square root, but because we're squaring the magnitude, we don't need that. So remember, it's the X value squared. So B1 minus A1 is our X value, so squared, plus B2 minus A2 squared, plus B3 minus A3 all squared. Okay, so that is a way to represent this AB all squared. Okay, so now we're going to find another way to represent OA squared. So the magnitude of OA squared can be rewritten as A1 squared plus A2 squared plus A3 squared. And the magnitude of OB squared is B1 squared plus B2 squared plus B3 squared. Okay, now one more thing we're going to represent is, let's remember our dot product. So A dot B, recall, is the magnitude of OA times the magnitude of OB times cos theta. Okay, or we can say that OA times OB times cos theta equals A dot B, either direction. Okay, that might help you, because check this out. Right here we have OA, OB, cos theta, so that can all just be represented with the dot product. So with all of this information, we can rewrite this equality statement using all of this stuff. So on the left side, okay, I hope we have room for this. we have this here, this b1 minus a1, okay, because it's ab all squared, so we're replacing it with that. So I'll try to squish it in. Okay, and then that will equal, hopefully you have more room than I did, OA squared, which is A1 squared plus A2 squared plus A3 squared, plus OB squared, which is B1 squared plus B2 squared plus B3 squared, minus 2, and then A dot B. Because this OA/OB cos theta could be rewritten as just A dot B. So for us to actually do this, I'm not going to show it all. You would expand, collect like terms, and you would isolate the dot product A dot B, and then you have it all in terms of these variables, which are, these numbers, which are just the 3 coordinates. And what you get when you do that, which I'm sure you believe me, but if you want to do it on your own, it's actually a pretty fun exercise. It's not too bad. You have that the dot product between 2 algebraic vectors is just you multiply the x values together, and then you plus multiplying the y values together, and then you add multiplied of the z values together. And that is it. So super simple example. If those are your 2 vectors, and you should put vector signs over top, then A dot B, well, you just do 5 times 3 plus 2 times -2 plus 1 times 0. So the 2 x's together plus the 2 y's together plus the 2 z's together. So 15 minus 4 plus 0 is 11. So that is the dot product between 2 vectors. Okay, so we're going to prove that this distributive property still holds. Okay, so let's just make that A is equal to A1, A2, A3. And let's make it that vector B is equal to B1, B2, B3. And that vector C is equal to C1, C2, C3. Okay, then let's start with A dot B plus A dot C. So then that would be A1, B1 plus A2, B2 plus A3, B3 plus A1, C1 plus A2, C2 plus A3, C3. Okay, so now we can use the commutative property and move this A1, C1 so it's next to the A1, B1, etc. So we're just using commutative property here. And then A2, B2 plus A2, C2 plus A3, B3 plus A3, C3. Okay, so now notice these 2 groupings, you can common factor out A1, and then you're left with B1 plus C1. And then you can common factor out an A2, left with B2 plus C2. And then common factor out an A3, and you're left with B3 plus C3. So notice that this is just the dot product of A dotted with the sum of B plus C. So this proves the the distributive property. All right, so we can also use the dot product to find the angle between 2 vectors when all we know is their coordinates. So that is actually very useful. So if we have theta between 2 coordinates, so all we know is that B is B1, B2, B3, and vector A here is A1, A2, A3. Well, we know that the dot product from before is just the magnitude of A times the magnitude of B cos theta. So now we can just rearrange that cos theta is the dot product divided by the magnitude of each vector multiplied together. Okay, so we can find the dot product and the magnitudes just with the coordinates. So that's a pretty useful thing. We can find the angle between any two vectors in R3 with just their coordinates. So let's do that. So first let's find the dot product between these two vectors. So it's -1 times 3 plus 2 times 4 plus 4 times 3. And that gives us 17 when we add that and collect. Okay, so that's the dot product. Then remember the magnitude of A is just the square root of -1 squared plus 2 squared plus 4 squared. So that gives us root 21. And using the same process, the magnitude of B is root 34. Okay, so then we have cos theta is equal to 17 over root 21, root 34. So notice I'm leaving these as roots because those are exact values. When you do the inverse of cos, you get approximately 50.5 degrees between those two vectors. Okay, so we can also use the fact that the dot product is 0 between perpendicular vectors to solve problems. So if these two vectors are perpendicular, let's recall that their dot product will equal 0. So therefore, we can set our dot product m times m plus m times -3 plus -3 times 6 equal to 0 and just solve for m. So this just gives us m squared minus 3m minus 18 equals 0, which is factorable to m minus 6. M plus 3. So you get m equals 6 or -3. Okay, so either one of these values would make these two vectors perpendicular. If you couldn't factor here, you could also use quadratic formula. Okay, example 4, a parallelogram has its sides determined by A, 6, 1. So say 1, 2, 3, 4, 5. Okay, so 6, 1 then is here. Okay, so you use a ruler unlike me here. So there's A, and it's equal to 6, 1. And then B is -1, 3. Okay, determine the acute angle between the diagonals of the parallelogram. So let's continue the parallelogram here. And the diagonals would be here and here. So the acute angle is this angle theta, is what we're trying to find. So let's label this point C. So notice that vector OC is just A plus B. So it is just 6 minus 1, so 5, and 1 plus 3, 4, so 4. So the coordinates of this are 5, 4. That is a vector OC. Okay, and then vector OD, sorry. So yeah, so OC is what we want here. So we need to know the angle between this vector here and this vector here, which is BA. So BA is going to be equal to its position vector OD. So if I draw vector OD here, the angle that we have right here, these two angles are equal. So if we find OD, which is just A minus B, okay, so 7, -2. So now we just need to find the angle between OC and OD. So that is equivalent between OC and BA, since BA is a position vector with OD. Okay, So cos theta is equal to the dot product of OC with OD divided by the magnitude of OC and the magnitude of OD. So this dot product becomes, so it's 5, 4, dotted with 7, -2. And then we have the square root. This magnitude of OC is root 41, and the magnitude of OD is root 53. So when you do this math, so 5 times 7 is 35, minus 8. So 35 minus 8 is 27 over root 41, root 53. So when you solve this for theta, you get 54.61 degrees. Okay? All right, so find a vector or vectors perpendicular to both A and B. Okay, so we're going to say let the required vector be vector x, which we're just going to call x, y, z. Okay, so this is the vector that's perpendicular to both. So if it's perpendicular to both, then that means the dot product of A dotted with x will equal 0, and B dotted with x will equal 0. So let's go ahead and actually do that. So 1, 5, -1 dotted with x, y, z has to equal 0. So x plus 5y minus z has to equal 0. Similarly, over here, -3, 1, 2 dotted with x, y, z has to equal 0. So -3x plus y plus 2z equals 0. I realize this 2 and this z look the same. Sorry about that. Okay, so now we have two equations and 3 unknowns. So I'm going to call this equation 1 and this equation 2. So I'll change color here. So what we're going to do is we're going to represent two coordinates in terms of the third coordinate. So represent two coordinates in terms of the third coordinate. Okay, so we're going to multiply equation 1 by 3. So 3 times equation 1, and then we're going to add 2. So 3 times equation 1 is 3x plus 15y minus 6 equals 0. And then we're going to add it to equation 2. Okay, so we're just doing elimination here. So minus 3x plus y plus 2z. Sorry, that shouldn't be minus 6. That should be minus 3z. I actually have a mistake on my note. There. Okay. So when you add this together, you get 16y minus 3z plus, so minus z equals 0, or z equals 16y. Okay, so we're going to leave that as important. And then we're going to sub that into equation 1. So then you get x plus 5y minus 16y equals 0. So you can simplify this to get x equals 11y. So this gives you the coordinates 11y, comma, y, comma, 16y. So how does this actually solve the problem? Well, this represents, okay, sorry, I should say that y cannot equal 0. This represents a set of vectors that are perpendicular to the plane created by A and B. So if you let y be anything you want, you'll get an infinite set of collinear solutions, okay? So here you can see what I wrote, okay? So again, actually I'll write it down here. You guys should copy this down. So this represents a set of vectors perpendicular to the plane created by A and B, by vector A and vector B. So let y be any real number, y but not 0, to get an infinite number of collinear solutions. So for example, if you just let y be 1, then you get the vector 11, 1, 16. So that is a vector that is perpendicular to both. Okay, or if you let y be 2, you get 22 to 32. That vector is also perpendicular to both A and B. It's just longer than the first vector I mentioned. So hopefully you can re-look at this example, ask me questions tomorrow to clarify anything, and hopefully get all of these examples to make sense to you. So thanks for watching. Hope you learned lots.